Hello, and welcome to a new lecture of our module Decision Making for Autonomous Robots. My name is Marija, and in this lecture we cover methods for robot decision making, accounting for different sources of uncertainty. Our goal in this lecture is to develop powerful, fully probabilistic models for robot decision making that allow robots to reason and perform actions even in highly uncertain and unstructured environments. To do this, we'll build on ideas from the Markov decision process with complete observability and also extend it to include observation noise. This gives rise to a new framework for decision making called the partially observable Markov decision process, and towards the end of the lecture we then cover solution techniques for finding the best actions within this framework. So let's start with our problem setup. In this lecture, we're concerned with the problem of sequential robot decision making. Here, we have a robot that needs to find the best sequence of actions to take in order to maximize the expected future reward. This is the reward or the feedback that the robot gets from executing that sequence from the environment. So for example, say we have a mobile robot in an unknown environment that needs to explore it and maximize the coverage using its sensors. This robot might have several candidate trajectories that it can follow. And the goal of sequential decision making is to figure out which trajectory serves best, leading to most gathered information about the unknown environment. We can already intuit some of the key challenges associated with solving this problem. So first of all, we have the fact that subsequent actions in the future might rely on what has happened in the short term. So say the exploration robot has visited a location early on in the mission. Perhaps at a later stage, it gains less value from revisiting that location because it has already acquired exploration information there. And so we need to design decision-making algorithms that are not nearsighted, but actually have a sufficient horizon, look ahead, and predict what will happen conditioned on the short-term observations. Similarly, the robot needs to reason about the consequences of its short-term actions. For example, if the robot moves to a corner nearby and explores it, it might get a lot of reward or a lot of useful information in the short term. However, this might be less promising in the long term because it might get stuck there and not be able to explore more distant areas in the environment without significant backtracking. And so in sequential decision making, we need to develop algorithms that tackle these challenges and also are able to reason about actions over a sufficiently long-term horizon. In decision making, to remind ourselves, we formulate the problem using this interaction between the robot or the decision-making agent and the environment it operates in. So in our introductory lecture to decision making, we said that the agent can perform an action or makes a decision about something to do in the environment. In turn, the environment emits a new observation to the agent as well as a reward. The observation correlates to the agent's state, so it tells us something new about the state, for example, the location a mobile robot could be in. And the reward is a fundamental quantity in decision making. It's like a feedback signal that tells us how successful or how useful this action was that the agent just performed. And our decision-making loop was essentially this continual interaction between the agents and its environment. And this defines a so-called episode or the experience of the agent, which we can then study and figure out which actions lead to the maximum expected total reward in the future. Remember, this is the objective of the sequential decision-making problem. Now, in this simple diagram, we can see a relatively easy to understand interaction where the actions, observations, and rewards are represented simply using random variables. And this is fine, for example, if we have some deterministic behavior of the agent and its environment, and we can easily determine the realizations of each of these variables. However, what if they come from a probability distribution due to different sources of uncertainty in the environment? So as we said, real-world environments are imperfect and often incorporate different sources of uncertainty. And in this lecture, we want to see how we can actually bake them in our decision-making framework. This is our motivation. So where does uncertainty in the real world actually come from? Well, it can come from different places. First of all, uncertainty can come from the environment itself, or the world in which the agent is operating. Some environments, for example, assembly lines, can be very predictable and structured, whereas others, such as highway lines or pedestrian crossings, can be very unstructured or even dynamic, meaning that they change over time. And if these issues influence our decision-making process, we need to figure out how to incorporate them into our algorithms. Uncertainty can also come from the other side, from the robot. So because each action of the robot is associated with physical performance of something in the real world, for example, a movement, we often have actions that rely, for example, on the robot's motors, which are imperfect. For example, some actions may take time to execute, or may even fail completely, so that the agent doesn't end up in the state that we think it will end up in. Actuators, such as motors, can also be noisy. So you can think, for example, about the robot that we command to move forward. If its actuators are very noisy or imprecise, the robot may not steer correctly and end up somewhere on the left or on the right. And so this could be potential sources of uncertainty, which, if we condition next actions based on our ideal representation of the robot's behavior, might turn to be inaccurate. Uncertainty can also come from the robot's sensors. The robot sensors, such as cameras, are limited in two ways. First, sensors often have a finite range and resolution, which is depending on the physical structure of the sensor. For example, if we think of a camera mounted on a robot and the robot receives an image from it. This image has a fixed resolution, and each pixel in the image corresponds or can be projected into a physical distance in the real world. And therefore, because of the structure of our camera and the way the sensor behaves, we can't obtain higher fidelity or higher resolution measurements beyond those limits. Similarly, sensors are often limited in range. So for example, if we think of a laser scanner, on the other hand, often it comes with a specification sheet that tells us what is the maximum distance at which a point might be registered, because these sensors, due to physical limitations, can't sense at infinity. On the other hand, sensors can also be noisy or imprecise. These are random perturbations due to the imperfect nature of the sensor construction. For example, pixels or points that we register might not be exactly to the physical, corresponding to the physical quantities of the real world. Finally, we have sources of uncertainty coming from modeling errors. So when we develop decision-making algorithms in robotics, we often rely on models, which are, after all, abstractions of the real physical world. There is only so much that we can capture about the physical world in our models, because they're based on mathematics and also cannot cover all possible cases. We might also have to make some approximations in order to allow them to run on our actual robots with limited computational resources. So these approximations and these modeling errors might be quite substantial, and we might need to take them into account again in our algorithm somehow. We need to be mindful of the fact, what are the limitations of our actual models, in other words. So all of these sources of uncertainty motivate an approach to robotics that is probabilistic. So in probabilistic decision-making, we don't consider deterministic behavior where we know exactly what is going to happen and we can plan and make decisions in these types of frameworks. Instead, we're going to take a different approach and think about the probabilities of things happening or the robot being in a particular state, and then use that as a basis of more reliable decision-making that actually can incorporate some of these sources of uncertainty and lead to better behavior. That is essentially the motivation behind this lecture. And as we will see, including sources of uncertainty and adopting a probabilistic approach can come at the expense of significant computational complexity. So when we develop algorithms, we need to be conscious of the fact that we have to trade off this real-world kind of aspects as well as how much they actually cost to implement on real robots. So in this lecture, we group the sources of uncertainty in two ways. First, we have the uncertainty in action. So this is the actuation uncertainty. So if we tell essentially the robot to move to another location, how certain are we that the robot has actually reached that location? So a simple example is again the one of steering, where if we tell the robot to move forwards, this might not be happening in the physical world if sources of uncertainty and actuation are present. And then on the other side, we also consider uncertainty in the observations. Remember, observations are something emitted by the environment, something that the environment tells us about which state the robot is in. This could be as simple as which state, which location in a grid the robot is in. So if the robot is able to sense a wall, for example, it could infer that it's actually close to a corridor or the edge of a room in an environment. So there is a relationship between observations and states. Now, in our previous introductory lecture to decision-making, we built the Markov decision process, which was concerned with actuation uncertainty. And as we refresh on the next slides, we modeled this using a stochastic transition model between states. So if the robot is in a particular state and performs an action, we actually had a probability distribution for it ending up in a subsequent state. In this framework, we assumed that observation uncertainty was not present or that the robot's state was fully observable. Now, in this lecture, we're going to go a step further and also think about the second aspect. So we say, what if we actually have sensing or actuation uncertainty? How does this influence our decision-making framework? So in addition to having actuation uncertainty associated with the robot's movement, we're now saying that we're not exactly able to correlate the observations that we get from the environment to the states, not on a one-to-one deterministic basis, but we actually have a probabilistic model there too. So let's build this up by looking at some examples and illustrations in a little bit more detail and understanding the different sources of uncertainty and how they influence planning and decision-making. So we revisit our familiar robot example where it has several different possible waypoint trajectories to follow. So first, in this module, we consider the planning problem, which we do not consider uncertainty. And so in the planning problem, we said we construct some sort of graph through the environment, for example, using a sampling-based approach. And then we follow the edges of this graph and the vertices in order to find a particular path that the robot should move through. So remember, we had a graph consisting of vertices, which are collision-free configurations in the environment, and edges, which correspond to collision-free paths. And the planning problem was all about how should we connect these vertices together, these states, via the edges in order to solve a path planning problem. This is specifically in the context of classical planning. We thought about the shortest possible path connecting two different points. And importantly to realize here is that our planning problem did not explicitly incorporate any sources of uncertainty. So when we established this graph, that was basically done. We did not consider the possibility that these vertices are not exactly true or safe in the physical world, other than by incorporating some heuristics, such as inflated radius of the robot. Instead, we said that these configurations, for example, that we sample, and these collision-free edges that we check, we relied on our model to give us that information. So we did not include probability. So for example, on this graph, we have different vertices corresponding to the robot states or nodes, and we have the red edges connecting them. And so in the super simple case, if we say we want the robot to move from S1, where is the root of the tree, to another state S2, we said that the probability of the robot executing that motion successfully with respect to our graph was 1. So each time that we plan a path through a graph, that path was assumed to be perfectly executable without any sources of uncertainty. Obviously, there are limitations to this approach. For example, if the robot actuation is uncertain, then the robot cannot be guaranteed to actually end up in S2, assuming that it started as S1. And this was exactly our motivation behind the Markov decision process, or the MDP. In the Markov decision process, we said that now we actually have actuation uncertainty. So remember, we can't be perfectly sure which state the robot will end up in next. And so now we developed this general framework for decision making that also accounts for actuation uncertainty to therefore make it more robust with respect to the planning approaches. So again, we can consider this graph, and just as a brief recap, we formulated the MDP using a set of tuples corresponding to the states in our decision-making process, the possible actions that the robot can take, the probability transition matrices, which is a stochastic representation of the state transitions, and the reward function, which tells us what is the value of the robot executing particular actions from particular states. So important thing to note here is that our state transition probabilities here are actually stochastic. So we have some model telling us how successful certain actions were from states. And so if we were to look at how this looks in our simple tree here, then we say now, perhaps if we tell the robot to move from S1 to S2, this could happen with a probability of, say, 0.5. But if, for example, the steering is unsuccessful, the robot could also end up in S3 or S4 with a probability of 0.25. So we could look at this transition model and figure out probabilistically where we expect the robot to end up in next, assuming the actuation uncertainty. So essentially what we do here is also account for the fact that now in our graph, we're not sure that these edges can be perfectly executed by the robot again. And now what we're going to do in this lecture is also take it one step further and think about what happens if we also have observation uncertainty. Now, intuitively, observation uncertainty is all about figuring which state we are in. So assuming that this transition has happened over here, and the robot has ended up in one of these states, in the MDP, we assume that we had access to an observation that tells us which state that the robot is in next. So if we were to freeze our decision-making process after this action has been executed and look at the observation that the robot receives from its sensor, then we would be able to say with confidence which actually of these states the robot is really in. However, in the partially observable Markov decision process, or the so-called POMDP, we now relax this assumption. So now we actually have both the actuation as well as the observation or the state uncertainty. So going back to our framework formulation, in the POMDP, we have the state's actions, the state transition probabilities corresponding to actuation uncertainty, of course the rewards capturing the objective of the decision-making process, and now we introduce additional variables as well. So importantly, now we have this omega, which we get back to later, corresponding to the set of possible observations. And also we have O, which is the observation model, which tells us what is the probability of the robot receiving an observation given that it is in a particular state. So partial observability here really refers to the idea of state uncertainty. Our states are now not fully specified, but rather partially observable due to this new source of uncertainty. So let's see how this looks in our tree example now, just to get an intuitive feel. So now, if the robot follows the same assumed stochastic state transition model with the actuation uncertainty, we have the same probabilities as before that come from the probability transition behavior. But now, additionally, we also have possible observations that the robot can receive. So if we end up on one of these states and receive an observation, we're only able to say what is the probability that this observation was received in a given state. So say we receive an observation O. Here we just consider one observation for a simple example. In the next time step, we don't know which state we're in. We just know the observation that we received. And then we can consult our model in the POMDP to figure out the probability of having received that observation in any of these states. So to recap, now we have two sources of uncertainty. First of all, the actuation uncertainty coming from the state transitions. And secondly, the observation uncertainty that's coming from the relationship between the received observation and the state. And in the POMDP, which is partially observable, we actually do not have explicit access to the state that the robot ends up in. And we have to develop a decision-making strategy that accounts for both of these uncertainties. And this is exactly what we're going to do next. In the next part of the lecture, let's go deeper into the mathematics of the partially observable Markov decision process, or POMDP, and discuss its properties. To start, let's revisit in more detail some of the content we presented in the lecture on simply Markov decision processes, or MDPs. We designed the MDP as a general framework for sequential decision-making accounting for robot actuation or state transition uncertainty. The MDP was based on several important assumptions allowing us to carry out decision-making in a mathematical way. Importantly, first in the MDP we said we always have a fully observable environment. By this we mean we always have access to the robot state via its observations. In other words, if we know the observation the robot receives from the environment at a particular time, we automatically know its state. There is no ambiguity associated there. Secondly, the MDP was based on the assumption of Markov dynamics. As a recap, this simply means that if we know the state of the robot at a particular time instant, this is all the information that we need in order to execute the optimal actions in the future. So our best actions in the future do not depend actually on the history of observations and actions, only on the current state. And this allowed us to decouple the problem and solve it iteratively using value and policy iteration. Next, we assume that we have stochastic transitions, and this is where the actuation uncertainty comes in. So we have a probabilistic model of how the robot state evolves, assuming we execute given actions. And our final assumption was that the policy of the MDPs are stationary. So in other words, they do not depend on the particular time instant during the missions. The optimal policy will always be the same if the conditions of the MDP are the same. So going into the mathematics of the MDP in more detail again, the MDP was defined by a tuple where we have several different elements. So first we have the finite set of discrete states that are present in our MDP. This could be, for example, cells of a grid in which a robot is navigating. Then we have a finite set of actions that the robot as the decision-making agent can perform, such as deciding which cell to move to next. Thirdly, a key element was this state transition probabilities, which simply tells us what is the probability of ending up in a next state, assuming we are currently in a state and take a given action there. So in our MDP lecture, we actually enumerated these state transition probabilities for a simple problem and showed how the state evolves probabilistically using the transition model. And finally, in order to be able to carry out decision-making in an MDP, we also consider that we have a reward function. So what is the expected reward that the robot gets, assuming it is in a state and executes a given action? This reward, remember, is an important element that tells us the success of executing an action in a state, and we use the reward as a signal in order to find the optimal policy we then learned in the MDP. So this is our definition of the MDP, and now if we want to extend it with these ideas of partial observability in the POMDP, let's see how our definition will actually change mathematically and how we need to modify it. So the POMDP is actually rather similar to the MDP, with a very slight extension to account for this observation uncertainty. So in the version of the POMDP, we have everything being the same. We still have the set of states of our POMDP and actions. Again, with actuation uncertainty, we also have the state transition probabilities, as well as the reward function. However, now importantly, we have a finite set of observations and observation probabilities as well. So we have to add two new elements to our tuple. The finite set of observations is simply the list of all observations that the robot can receive from this environment. It's also a discrete set. And the observation probabilities are simply the probability of receiving an observation given that the robot is in a state having executed a particular action. And here we set the time subscripts in order to reflect the notation, the convention that we're following, that each increment of the time step occurs when the environment acts back to the agent. So when the robot executes an action, it ends up in a state and receives an observation. So this is why over here we incremented the subscript. So these two new elements, importantly, allow us to incorporate this partial observability. So now the state is a hidden thing in our POMDP, and we look at the observation and the model that we have associated with observation probability and try to infer which state that the robot is actually in. So previously we had a deterministic observation given by the complete observability of the MDP, and now we actually have a new set of probabilities, a new probability space that we're trying to put in our POMDP and see whether we can actually make decision making work in this way as well. So one question that we might ask ourselves at this point, having looked at the mathematical notation and understood that we have now observation and state transition probabilities playing together, we might ask ourselves, is the POMDP still obeying Markovian dynamics that we need to perform decision making using dynamic programming approaches as in the MDP? And this is a very important question that we come back to later. So does the history now start to influence our next decisions? Do we need to keep track of everything we did in the past in order to plan for the future or not? To answer this question, one key concept that's very helpful to introduce at this point is the idea of a belief state. So now we're trying to rework our POMDP a little bit to make it easier to work with for decision making. And this is where this belief state comes in. A belief state is nothing but a probability distribution over the possible discrete states in our POMDP. So if our state here is S, we say that the belief of state S is simply the probability that the robot is in that state. So previously in the MDP, we didn't have this probability distribution because we always knew the state. But now we try to apply ideas from probability into the state and see whether we can reformulate the POMDP. So the belief tells us the probability of being in a state. And obviously, if we sum the beliefs of all the states that we have in our POMDP, then we would expect that they would equal to 1, since the robot must actually be in only one of these states. It follows naturally from that the belief state space is simply the set of all possible probability distributions, or the state of all possible beliefs. And now we see we have a much more complicated mathematical formulation compared to the MDP, where the state was known, but we're trying to make it easier to work with by introducing this concept of belief, where we have a probabilistic state now. So to make this more concrete, let's look at a super simple example where we have a POMDP with just 2 states. We have state S1 and S2. And the belief state space for this simple example can be simply represented using a line segment going from 0 to 1. Why? Well, if we know the belief of being in S1, let's say it's probability P, then the belief of S2 will simply be 1 minus P, because as we said, the probabilities need to sum up to 1. So say this belief state space simply represents the possible values that P could take. So when P is 0, and we're over here all the way on the left side of our belief state space and the start of our line segment, then we say that there's 0 chance that we're in S1 and we are in S2, because 1 minus 0 is 1, obviously. And on the other extreme, we have the belief of S1 is 1, so we are definitely in state S1. And this line segment is simply illustrating the spectrum of all possible intermediate distributions of these probability states. So we see how this simple 2-state POMDP has induced a problem with 1 degree of freedom. We only need 1 variable to fully specify the belief state space. And we can start to understand how this can generalize to higher dimensional spaces, where we will, instead of line segments, have different hyperplanes and higher dimensional spaces. And we always have the fact that for an n-dimensional POMDP, so with n states, we have a 1 minus n degree of freedom problem that we need to solve. So this tells us how beliefs of different states in our POMDP are actually related to each other and how they depend on each other using this constraint that the beliefs over all the states must sum up to 1. So now we understand what a belief is and how we can represent the belief at an instantaneous time instant. However, what if belief changes over time? So what if the robot starts to take some actions, receives observations, and following that interaction with the environment, how does the belief actually evolve? So we can go back to our line segment now and think about what will happen. So how would the belief change? This is just a simple intuitive example to understand the ideas behind the belief state space and its evolution. And then later we go into the mathematics and how this actually becomes useful when dealing in the context of the POMDP framework. So if we have some observations and actions, how does the belief change? This is the key question that we're trying to answer. So in this line segment, say we're over here at the yellow dot. This is the probability, remember, of being in state S1, which also by consequence gives us the belief of state S2. So here is one realization in our belief state space representing to our current belief. And now we have, say, two different actions that the agent can take, A1 and A2. And we have three different possible observations that the agent can receive, O1, O2, and O3. And these arcs here correspond to different realizations of the observation and action pairs. So on the bottom we have transitions associated with executing A1 and receiving three different types of observations. And on the top we have the same apart from with A2, the three observations corresponding to the other action. So depending on which action that the robot will select and the observation that it will get, we can see how the belief of S1 here will actually evolve. So without going into any mathematics, we can intuitively understand that the belief will actually change in one of these ways corresponding to one of these arcs. And again, we will always have the fact that the beliefs over all states in the state space will sum up to 1. So what this diagram is showing is that belief can actually be updated depending on what will actually happen at the next time step of the robot mission. So how can we formulate this mathematically? And so here is where our knowledge of probability will actually come in. How can we recursively update the belief? Is there an equation that tells us if we take an action and receive an observation starting from a belief, what the next belief will be? So this is what we try to answer now. Essentially, we can use our knowledge of probability and especially Bayes' rule in order to obtain the equations for doing just that. So assuming that we have a belief of a state here, just dropping the subscripts for clarity, then we can derive an expression which is very similar to a filtering procedure that tells us the belief of a given next state. And what this involves is actually summing up over all the possible states that the robot could end up in. And the reason we do that, again, is because the state is only partially observable. So intuitively, we somehow need to condition and take into account all the possible realizations of the next state when we try to calculate our next belief of a given next state mathematically. And here we have eta, a normalizing constant appearing in our equation, which will force our beliefs of the next states to sum up to 1. So the derivation for this actual equation is rather simple. It's based on ideas of probability, Bayes' rule, and can be found on the lecture slides towards the end without going into all the mathematical details here. The key thing to know is that we can actually perform a recursive update of the belief using an equation that actually only depends on the models that we have. So important thing to know is that in this actual expression, we just need to use our models for the observation and the state transitions. So if we have a table of these probabilities, we can plug them into our equation here and figure out our next belief. And the reason we are doing this is to see how our knowledge of the state evolves over time in a compact way. Now, the idea of recursive filtering and updating is starting to ring some bells. So if we think about how we update the belief here, given only the action that we have performed and observations received, then we can again start to draw a diagram like this. So over here, this is just a chain of states happening, receiving observations and executing actions. And looking at such types of structure and a recursive filtering, we actually notice that our belief update does not depend on anything in the past. So the actions that are going into our computation here and the observations being received are in fact not dependent on history now. So this is a very neat trick that we do in the POMDP, where we introduce this concept of belief as a compact summary. So this is one value that we need to maintain as a sufficient statistic that tells us everything that we need to know about what happened up to this point. And the diagram is simply a pictorial representation of that. We don't see any intercorrections between past actions and current actions and neither past observations. So we can look at this in terms of time step by time step following the recursive filtering procedure. And lo and behold, we actually have the Markov property again. So Markov property tells us that we can only look at the current state to plan for the future, disregarding the history. And the belief is, the belief ideas in our POMDP actually satisfy the Markov assumption. So we kind of keep track, back to our diagram of the belief, we kind of keep track of these arcs, updating the belief, and the belief somehow stores everything that has happened up to this point in a compact way. We don't need to keep track of the history. So now that we have something with the Markov property, we can think about how to formulate this again as a third kind of MDP. So in the belief MDP, rather than having a finite set of states, as in the classical POMDP, we have reformulated with an infinite set of beliefs which correspond to the probability of being in those underlying states. And the reason why we have reformulated our POMDP in this way is because we have direct access to these beliefs and keep track of them, rather than being in hidden states that we can only access through our observation model. Moreover, our beliefs lend themselves to the MDP formulation because, as we just saw, they obey the Markovian property in terms of their transitions. So by using the recursive filtering, we can now morph our POMDP into the MDP formulation and see what a possible approach could be to solve it using our MDP techniques. So in the belief MDP, we have an infinite set of beliefs. We have a finite set of actions, which are the decisions that the agent can make from one of these states. And this is exactly the same as in the POMDP or the MDP. And then importantly, we have also reformulated our state transitions in terms of the beliefs. So if we look at the equations on the previous slide, we can adapt it in order to express the transition probability of ending up in the next belief of a given state, given that we have a current belief on a state and perform a given action. So this is essentially the analog of the state transition in the MDP and the POMDP, except now we want to account for this probabilistic belief variable that we introduced. So going into the mathematics again, we can see that the belief state transition probability depends on two different terms. So one of the factors is simply an indicator that tells us that if we have a belief update that actually leads to the next belief, then the belief state transition probability will be non-negative. And the second term is simply the normalizing constant that we obtained from the previous slide in the recursive belief update. So using the laws of probability and conditioning, we now have the belief state transition probability, which tells us how belief evolves over time if we execute action. So this is what these equations here are trying to say in our belief MDP. And the final component of our belief MDP is the reward function, which is now defined on the belief states rather than the discrete states as we did before. The reward function in the belief MDP amounts to therefore taking the expectation of the regular reward, which depends on the discrete states in action. We need to take the summation with respect to all the possible states that we might end up in and their beliefs. So essentially in the belief MDP, we need to average all the possible rewards that we could get in the future given our knowledge of the current belief. So if the probability of being in a particular state is high, then the reward corresponding to that state, given that we have taken an action, will be weighted more highly in this expectation term. So to summarize, what we have done here is started with the MDP, which only accounts for actuation or state transition uncertainty. Then we added partial observability, which says that we have a probabilistic relationship between the robot observations as well as the states, which are now only partially observable through the observations. Then we introduced this concept of a belief, which is the probability distributions over states. And by noting that our belief evolution actually follows the Markovian property, is independent of the history of beliefs, we obtained a reformulation of the POMDP called a belief MDP, which contains exactly the same elements as the classical MDP in the tuple, except now this time we're operating in the space of beliefs. And one very obvious thing to notice is that now our beliefs correspond to an infinite set rather than a discrete set of states as in the MDP. And we'll see exactly how this influences our solution mechanisms and what are some of the strategies we can go about that. Before we delve more deeply into the mathematics of POMDPs and ways of solving them, let's see an example of what a POMDP actually looks like in practice in an intuitive way. So for this example, we consider the classical tiger problem for POMDP literature, which is a very simple POMDP. So what is the tiger problem? Consider the following scenario. We're standing in front of two closed doors and we don't know what's behind them. What we do know, however, is that behind one door lies a tiger and the other one a treasure, but we don't know where they are. So if we open a door with a tiger, we could get scared or potentially eaten, yielding a very high negative reward. However, if we open the door with a treasure, we can get rich and obtain a positive reward. And the objective is obviously to open the door which contains the treasure. Now, what actions can we take in this situation? Well, we can open either the left door or open the right door. And another possibility we also have is to listen at either of the doors. And by listening, we can hear if the tiger is there. And this somehow gives us more information about this problem and way of solving this dilemma. So if we hear the tiger, we get more knowledge about the problem. So how do we formulate this problem setup in the POMDP considering all the components? So we have two states in the problem. Either the tiger is behind the left door or behind the right door. We have different actions, including opening the door or either listening. And we have different transitions associated with these actions. So if we listen, then we don't have any change in the state of the problem. The tiger is still behind the same door. And if we open one of the doors, we end the game and basically go back to the beginning. So we restart our problem if we choose to open one of the doors and see what's behind it. And the observations that we might obtain by listening gives us more information about the state. And these observations are that we either hear the tiger on the left or hear the tiger on the right. And the rewards that we could get in this problem is either we have found the tiger, it's a very high negative reward, we have found the treasure, a positive reward, or we have listened, which comes at the cost of a very small negative reward. So this is all the key elements of our POMDP formulated in this very simple problem. And let's have a look at the numbers and more details about how we specify the POMDP. So on the left, we can see ourselves in this dilemma, not being sure which door to open, and the two states we have. The reward function is as follows. So we have -100 if we open the wrong door, the one with the tiger. We have +10 if we open the correct door, the one with the treasure. And if we listen, we have a small negative reward of -1, which is like the cost. Now, for the observations, we can either hear on the tiger on the left or on the right if we choose to listen. So we have some observation models here. So this is this O term that came from the POMDP, which is telling us all about the probability of having received that observation, assuming that we're in a given state. So as an example here, if we have observed the tiger on the right, the probability of the tiger actually being there is rather high, so 0.85. So this somehow captures our intuition that if we have heard a tiger or think we have heard a tiger there, then there is a probability that the tiger is actually there. So we increase uncertainty. And here are the actions that we can take. Either listening or opening either of the doors, the three actions. Now on the right, we can see the state transition probabilities, just like in the classical MDP as well. So if we listen, we do not change the position of the tiger, so the state is still the same. So this is why we have these ones on the diagonal here. The tiger just remains in place. However, if we open one of the doors, then the problem essentially resets, so we go back to the beginning. And these capture the probabilities of states changing once we have performed a given action. So the state transition probabilities. So for the simple two-state POMDP, these are the observations we have, the actions, as well as the rewards. So now we have fully specified our POMDP problem. And in the next slides, what we're going to do is build a decision tree of how we can search this type of problem by investigating what happens if we perform certain types of actions and end up in different states or receive different observations. So the purpose of this example is to show how one can specify a POMDP and some strategies as to how much reward we can expect if we follow certain actions. So what we're going to do to investigate this POMDP is build a decision tree. A decision tree simply tells us the branching of possible actions that we can take from different states. So we're going to start over here at the top where we have an initial state where we don't know anything about the problem. So we have a 50-50% chance that the tiger is behind either of the doors. And so obviously the expected reward that we can get here is the average because we don't know anything about the problem. So either the tiger is behind one of the doors or the other, we have a 50-50% chance of encountering the tiger or the treasure there. So that's the root of our node, or a so-called initial state. This is where we start from. And now on the next layer, what we can do is investigate different types of actions. So if we open one of the doors on the left and the right, then assuming that we either found the tiger and the treasure, this will influence how much reward that we can get. And over here in the box is the next belief. So what we understand about the state next. So what is the confidence that we have about finding the tiger and the treasure behind either of the doors? So remember, on our state probability table, we said that our problem essentially resets if we perform an opening action. So this is all that the 50-50% chances are happening here. Now, what if we implemented a more conservative strategy and decided to listen? Well, if we listen, we have two possible observations that we may receive. So either we heard the tiger on the left or on the right. And this now will change our belief. So our confidence that the tiger is on the left or on the right, depending on which observations we have received. So this is exactly what this branch of the tree is trying to tell us, that if we perform a listening action, we actually update our belief or our knowledge of the state. So we perform some kind of information gathering action to give us more certainty about what is the actual state of the problem and which optimal decisions that we need to take. So now, moving on to the next branch, say that we listened and the game did not restart yet, but we have heard the tiger on the, behind the left door, and we just followed this one branch for now. So what we do here is just focus on this one branch. So we assume that we have heard the tiger on the left in the first branch and what will happen next. So again, we can go for the opening action, restarting our probabilities, or we can perform listening again and do more information gathering to get us even more confident about where the tiger could be. And now that we have a greater depth of our decision tree, we can figure out what is the expected reward if we execute one of these actions at that particular depth. So, for example, now that we have knowledge from the listening step, our reward is actually unbalanced. So our expectation is now conditioned on the fact that we actually listened in the previous step. So now, instead of multiplying this 50-50% probability of the tiger and the treasure being either or, we have more confidence as to where we might find the tiger. So we used our observation model. Remember, 85% that the tiger is in the left side of the door if we have heard it there. And then we can use that and propagate our expected reward. So remember, in the POMDP, we had that expected reward that arose from multiplying all the belief states by the regular reward from the NDP, and this is exactly what we're doing here. So we're multiplying our understanding of the environment. So what are the chances that we might actually obtain this reward, given that they were updated on the previous listening step? And now our rewards actually change. So instead of being -45, we know nothing about the problem. If we open the left door and have heard a tiger there, our reward actually became more negative, so -83.5. And this reflects the fact that we're now opening a door intuitively where we have heard the tiger, which does make sense. And for this simple problem, we can keep going and we can say, okay, let's say we listened again, and the next states would follow from that, and so on. So now, even on that reward, if we have heard the tiger the second time, our expected reward has further decreased to -95. And so over here, we're almost converging to the actual rewards, assuming that we have gathered enough information about the tiger being on the left, that it's actually -100, which is the reward that we would get, assuming we knew for sure that the tiger is in that location. So this decision tree stresses several important things about the POMDP as a structure. So first of all, it shows us the interplay of these probabilities, and especially how rewards come into play. So we're basically updating our previous knowledge with new information, and we somehow use the probabilities from the tables that we saw on the previous slide in order to get new information, and it all follows a smooth mathematical way. And that's the first thing. And then the second observation is obviously that this POMDP is rather huge. So even with these two simple states and actions, two actions of which actually reset the problem, so we don't need to consider them in that great detail because we just go back to the beginning, we just branch out exhaustively because we have this uncertainty and we need to incorporate all that in our decision-making framework. So if we want to make several actions over several states and we have a very high horizon over which to plan, we can see how this can get extremely computationally expensive. And so going back to what we said, all this consideration of uncertainty and probabilistic treatment comes at a very high computational expense. So the more accurate that we want to get to the way the real world is behaving, we need to make some sacrifices in terms of efficiency. And so this simple example motivates efficient methods for solving POMDPs in practice and how we can investigate them. So finally, we move on to the decision-making part of the lecture and learning how we can solve problems formulated in the POMDP framework. Our goal here essentially is to learn and figure out the best actions our agent should take in order to maximize the value of expected reward it gets in the future. Now, before we move on to the solution techniques, it's worth mentioning at this point that solution methods for POMDPs are a very broad field of study and also rather mathematically involved. So the methods that we cover in this lecture are suited for the time that we have as well as for the rest of the content of this module. However, they're certainly not restricting the ways in which we can solve POMDPs, and we mentioned some alternatives towards the end of the lecture. So talking about solving POMDPs, what does the solution actually look like? So here again, we revisit the content from our MDP lecture, where we formulated decision-making as a policy. Remember, a policy in an MDP is a rule book of what the agent should do should it find itself in a particular state. A policy pi was a mapping of the agent's state to its actions. And remember, the optimal policy was the best actions from that state that leads to the maximum expected cumulative reward in the future. For POMDPs, we developed the exact same ideas, except this time referring to these beliefs rather than the discrete states. So a POMDP policy essentially maps the state beliefs to actions. So if we have a belief, remember a belief is a probability, then we can look at our policy and see which action should we take there. This is exactly the same as the MDP, except substituting the state with the belief that we now have from our belief MDP. An optimal policy, therefore, is, as expected, one that yields the highest expected reward in the future from any belief state. So pi star here, or the best possible policy that we have, is the action that we can follow given a certain belief that will give us the maximum reward in the future. So essentially, we're just developing the analog of everything we knew about MDPs in this new POMDP or belief MDP formulation. So continuing with that logic, we can also revisit our Bellman equation ideas and apply the principles of recursive decomposition in order to find Bellman's equation. So remember, Bellman's equation simply told us that the value of being in a particular state, or for the POMDP a belief, is the reward that we get for executing the next action plus the value from the state, or in this case the belief, that we find ourselves in next. And so basically we just broke the problem down into the next reward that we get and the ones that we get from the future. So that's just a recap of what the Bellman equation tells us, and for POMDP it's formulated with respect to these beliefs. So we also here need to sum up over the possible observations from the observation space that we have, because now our observations are not deterministic and we actually have this observation model coming into play to capture the state uncertainty. So our Bellman equation for POMDPs is developed exactly in the same way as for MDPs. So far, so good, or that's what we think. This is where, unfortunately, the similarities end, because at this point we realize from our belief MDP formulation is that our belief is now a continuous value. So previously we had this reward associated with discrete states and actions, and now we find that everything depends on continuous beliefs rather than discrete states. And therefore, if we want to try dynamic programming methods, such as value iteration or a policy iteration that we encountered in the MDP lecture, we find that this is very difficult because the robot can essentially end up in this infinite space of continuous probabilities. So how do we cater for that? Unfortunately, this means that POMDPs are in essence a very hard problem to solve, especially when the number of states is large. And we already saw in our tiger problem example how difficult, even with just 2 states, it gets if we try to search the space of all possibilities. So what can we do? One idea is to use some approximation methods and only consider a subset of beliefs. But what we're going to do in this lecture is just try a slightly different approach that's also in line with the rest of the content of this module. So rather than using dynamic programming, we're going to see if we can follow a slightly different strategy and find the optimal policies. The approach that we discuss in this lecture is based on the idea of forward search. So say we have this tree corresponding to a branching of our actions and our observations, and we don't know about the problem because we haven't acquired any experience from the agent yet. So what we can do is try to search over different experiences or sequences. So say we start at the top of our tree, of our POMDP, and we run a sequence, for example, by observing experience or using a simulator. That tells us something about our problem space. And we want to see with this forward search paradigm is whether we can use what we learn from seeing these sequences unravel, whether we can find optimal policies in this way. This is just the basic idea, but in the next slide it gets more concrete exactly how this works. So we want to branch over actions and observations, see what happens, and use this as knowledge to develop our optimal policy. So here we can talk about what's called a T-step policy tree for POMDPs, which is nothing but, as we saw in the tiger problem, a branching over possible actions and observations. So over here, we say we have a T-step tree because our tree obviously depends on how many steps we can take. So on the bottom, we only have 1 step to go. We can take 1 action and the problem is over. So it's episodic. And earlier on in the tree, at the very root, we have T steps, and this is why it's a T-step policy tree. So we want to impose some kind of horizon, run a simulation or an experiment, see what happens, and then see whether we can use that information to find our optimal policy. This is the basic idea. So how does this generally work if we want to implement an algorithm that tries to explore this policy search tree? So here we're going to discuss a strategy called the Monte Carlo tree search, or MCTS. So first, the MCTS is based on completely observable environments captured by the MDP. So there's no partial observability happening here. This is just to illustrate how a tree search is actually useful in a simpler scenario. So assuming we know everything about the state. So basically here we simulate different episodes starting from an initial state, and we collect some rewards, collect some experience, and see how that would lead us to the optimal policy using this forward search paradigm. So here we see an example. So this is one of these trees that reflects what's happening with actions and observations. The blue dots correspond to actions taken by the agent, whereas the white circles correspond to different states. And here at the root, we're in our initial state, just like in the tiger problem and from the previous slide. And so we use a simulator in order to see what happens if we follow a sequence of actions and receive observations. So in this case, we end up over here on this leaf node. Our episode is complete. And we want to take that information and see how promising this path was. How can we update the tree, and how can we combine information from different simulations? Okay, so we have a tree, and what we're trying to do here is run simulations. This is called a rollout, and then collect that information and see what we can learn about the search tree. Actually, one parallel that we can draw here is these ideas that we introduce from Monte Carlo sampling in a reinforcement learning lecture. So remember, Monte Carlo sampling was essentially trying to use stochastic sampling strategy in order to estimate a deterministic quantity. So here we're doing exactly the same. We say that all the space of observation and actions is exhaustive and very computationally challenging to search. So we try to run simulations exploring different episodes and then use that in order to find the best policy. So using this tree structure and by following different branches, we have essentially circumvented the need to explore the full state of possibilities and made our problem much simpler. However, we need two things. One is the access to this rollout simulator, so something that actually gives us the experience or the episodes. And two, we need some way of actually, how do we select which actions to pick next? Should we do so randomly? Or should we implement some kind of strategy where we use some information that we already have about the tree and work with that as well? So in Monte Carlo tree search, we are essentially facing the problem of exploration and exploitation. We need to figure out how to grow this actual tree and which branches to pick in our simulation environment. So one could imagine if we were exploring the tree randomly, it would be hard to identify promising actions. However, if we were just going for branches that we already know are promising, we would not leave much scope to explore the problem space and execute random actions. So these are the two extremes we somehow need to trade off between using exploration-exploitation approach. So in Monte Carlo tree search, one value that we introduce for all the states or all the nodes is called the upper confidence bound. The upper confidence bound is essentially a value that tells us how promising a state is. So it includes two terms. One is the potential gain associated with that state or that node. So this tells us, given everything that we know so far, how much reward did we obtain by seeing the state before? That's the first term. So that's essentially this exploitation part where we try to give more value to nodes or to states that we have seen before and obtain high rewards from them. And the second term is an exploration term, which accounts for the fact how many times have we seen the state before, the natural log of that over how many times have we seen that state and executed the action under consideration. So what we want to do here is when the number of visitations is low, we give more value to this node because we haven't seen it many times before. And obviously we have to basically initialize these terms and make sure that we're keeping track of the upper confidence bound for all the nodes, all the states, keep propagating them. And then we look at this indicator and we say, this is how promising a particular state is, and this is the one that I should go to next, given this action. So to quickly recap, the Monte Carlo tree search is a method of exploring the possibilities of having different observations and actions, So we run simulations, we acquire some experience, and then we try to figure out what is the best policy. And this prevents us from doing an exhaustive search. And how do we actually explore this tree? Well, we use this upper confidence bound, which trade off between exploiting nodes that we know are good and exploring nodes that we haven't been to before. So this is what the equation is telling us, simply balancing these two aspects. So here's a picture just illustrating how the Monte Carlo tree search algorithm works. We have to select nodes based on the so-called upper confidence bound. So this is how we branch down. So we follow the policy and we can expand the tree with new actions as we encounter them. Always the upper confidence bound is actual value that's guiding our search and allowing us to decide what we're going to do next. And then when we finish the simulation, we can see the reward that we get in the end. And finally, we have a backpropagation step that tells us, okay, so we just followed this policy, we reached the end, we obtained this reward, and let's update it so that all the nodes that were in our path, we know how much reward we got in the end. So we try to average the values of whatever is already stored in this node with this new experience. And in Monte Carlo tree search, we repeat this many times until we can find a promising policy. Note that this is very different from the approaches of value and policy iterations that we encountered in the MDP lecture, because now we have this additional complexity of having many states, many actions, and possibly many observations. So this is the idea behind forward search. So how does this apply to the partial observability case with POMDPs? So in POMDPs, the equivalent of the Monte Carlo tree search strategy is called the partially observable Monte Carlo policy. And so essentially what we do here is we receive observations from the actions using a lightweight and very efficient simulator. So because POMDPs are so tricky and challenging to solve, one method is to rely on a very quick simulation. So what will happen if we observe this chain of events and then we use this to learn our tree? So for example, if we're playing a game, such as an Atari game, and we're not sure what the state is because of partial observability and we can only receive observations, the game simulator is actually a great way of learning about policies and our problem space without relying on physical, difficult to perform experiments. So often with POMCP, a simulator and an efficient way of calculating the branches of this tree, observing that experience is a key aspect. Now, in each node, in contrast to the Monte Carlo tree search, with the partially observable Monte Carlo policy, we want to store histories of observations and actions rather than just states. So this is exactly in line with what we discussed earlier about beliefs and histories. What makes POMDPs challenging to solve is that now we have this chain of events leading to a particular partially observable state. And we need to keep track of everything that happened. So with the belief MDP, we summarize this compactly with the belief. And with this tree approach, it's easy to store a history of everything that has happened rather than just a state to account for this aspect. So what we do with the POMCP is we modify our tree exploration search strategy to also account for the history rather than just the states. So this is the analog of a POMCP tree, very similar to the one from Monte Carlo tree search, where we again are using a rollout simulator, seeing what will happen, which reward we will get, and then backpropagating the values. Except this time, for each of these nodes, we need to store the history of everything that has happened when we follow that particular episode or chain of experience. and we select the next actions exactly the same way using an analog of the upper confidence bound. Remember, the upper confidence bound is a value that we store for each node, in this case each history node of our tree, that allows us to select promising next nodes to explore. So again, we have this trade-off between exploration, going to unvisited nodes, and we also have the potential gain based on what previous experience we have observed, and we come up with this value that allows us to pick next actions. So this is the same formulation, apart from this time we now see this H appearing rather than S. And the H corresponds to the fact that our nodes are now storing not only the states, well, not the states, but the actions and the observations which correspond to the history. And this is exactly because of partial observability, because we don't have access to the state itself. We only have access from a roulette simulator to the chain of actions and observations that we obtain from executing that policy and following our branch from the tree. And so this is just a conceptual overview of how these tree branch methods work and how we can use a forward view, backpropagate values, and try to figure out promising areas, promising branches, eventually converging to the best policy using the ideas of upper confidence bound as a sort of guide for our search. And so this is the approach to the POMDP solution that we encounter in this lecture. However, there are also other methods of solving POMDPs, as was mentioned. So unfortunately, due to their complexity, POMDPs are very challenging to solve exactly. However, exact methods do exist in a similar way to our MDP value and policy iteration. However, they're often very limited to a small number of states, just a handful, due to their inefficiency arising from our continuous belief space. Alternatively, we can play around with the fact that we have an underlying MDP behind our belief MDP, and we're trying to somehow figure out the relationship between our continuous beliefs and planning in the MDP itself in a classical way. So some approaches try to address the POMDP solution methods in this way. Another thing we could consider is point-based algorithms, which rather than considering the space of all possible beliefs in our POMDP, only consider certain points and work from there to find solutions. And finally, we can also try deep learning-based methods, for example, recurrent neural networks that also store a history of the time of everything that has happened when we obtain experiences or episodes for our POMDPs, and then leverage them in order to learn the optimal policy by seeing what the reward was. So the takeaway here is that POMDPs are very challenging to solve. We can use many different methods. The tree search method is very efficient because we don't have to explore the space of all possible combinations of actions and observations, but it does rely on having an efficient simulator to perform many different tests or experiments in our POMDP space and learn the best policy. Otherwise, the implementation basically amounts to running the simulator and picking the actions based on the upper confidence bound. There are also other solution techniques, and for these, the related work of this lecture is recommended to have a read through. So this brings us slowly to the end of our lecture on decision-making under uncertainty and POMDPs. So we first motivated the decision-making under uncertainty as a concept, where this uncertainty comes from and the different sources of uncertainty that we want to take into account in our decision-making tasks. Then we built on our ideas from MDPs and developed partial observability in the form of a general framework for decision-making under both actuation uncertainty and observation or state uncertainty in the POMDP framework. we discussed the relationship between MDPs and POMDPs there. Then we learned about the belief state space and how the POMDP can actually be converted to a belief MDP, which obeys Markovian dynamics that we need in order to do planning. So the belief MDP essentially operates by assuming a probability distribution over the discrete states of the core POMDP. And the reason for introducing the concepts of belief, as we said, is because it gives us a way of recursively updating the belief at every time step and alleviates the need to store the entire history of actions and observations, especially for decision-making problems. Finally, we had, after an example, an overview of some solution methods. So for MDPs, which are completely observable in the state, we introduced the Monte Carlo tree search method, which relies on a rollout simulator to simulate episodes of experience, figure out what the rewards are, and then backpropagate them into our policy search tree. And then in the case of partial observability, we introduced and discussed briefly the partially observable Monte Carlo policy, which essentially follows the same set of rules as Monte Carlo tree search, but operating in the space of histories rather than discrete states. But the basic idea behind these two solution methods is the same. We're trying to implement a forward view and learn about our problem space through experimentation. So on this topic, there's of course plenty of further reading that one can have a look at to learn more about POMDPs. Of course, the solution method for decision making one incorporates is highly dependent on the number of states and the problem structure. And therefore, if one ever needs to solve a POMDP in its raw formulation, then it's highly recommended to take a look at basically the readings and the different solution strategies that are available. Thank you for your attention.